We're going to discuss now our last example, which is related to air pollution and also connected therefore to chemical transformations. We're going to discuss the pollutant transport through air from plume emitting the pollutant to another point of receiving this pollutant. And we're going to discuss how the transformation of this pollutant affects the behavior. This example will help us to have a strategy to deal with models that are 1D models, which means that have a change also not only in time but also in space. But how can we simplify these models in order to solve them in terms of like a no D, a 0D model, right? So just to let's recall what are the 1D models. 1D models are the ones that includes one space dimension only, and this can be the distribution of a contaminant in soil, or can be seepage to the groundwater table, or evaporation as a function of the one space dimension, right? We also have processes in rivers that are being modeled in terms of based on 1D modeling. And we can have an image of a water level peak or a pollutant plume moving downstream. And this is the example that we're going to discuss today. So it is also related to air pollution modeling in only one direction. We have other examples, but we're going to remember this paragraph that was discussed in our one of our first lectures. 1D steady state models lead to ordinary differential equations. So that means that if we have a 1D model, we knew before that it means that we have a partial differential equation, because we're not only dealing with the change in time but also with the change in space. But if that change in space I mentioned, it's been at steady state conditions, it means that our differential equation has been simplified to just an ordinary differential equation. So we're going to now discuss a little bit about transport. So models with change in space are also connected to transport, to the term transport. Transport is a general term denoting processes which determine the distribution of biogeochemical species or heat in an environmental compartment. These transport processes are relevant in almost all environmental systems. There are two different types of transport processes, and these are the advection and diffusion. Advection denotes transport in the narrow sense. A particle is purely shifted from one place to another by the flow field. And while diffusion and dispersion are processes which originate from concentration differences. So this is our general equation of transport. And transport can be described by differential equations, right? That change in the three dimensions, in the x, y, and z. So also there is a change over time, right? The conservation of a variable a can be energy, or can be mass, or can be momentum, right? The change of this in time also includes the change in direction, and it also includes all the sources and things are gathering in this q variable, right? So JAX, JAY, and JAZ represent fluxes in the three space dimensions. The three flux terms are components of the flux vector corresponding to the three space directions. So in our example, we're just going to focus on 1D in one direction, okay? And this is just considering only 1D problem. So if we are if we make the decision to have this term, the term of the variation in space, only considering the steady state for this for the second derivative, which is this one, we can end up with an equation that includes the change on space, but as a function of time. And this is an ordinary differential equation, ODE model, as only time derivatives appear. I have moved from partial differential equations to differential equations just arbitrarily, just because we know that if once we have set the limits, we can already work on differential equations, right? So how can we can do this? Well, we can actually have formulas that describe how the variation on space occur, right? For instance, we can have the Gaussian distribution that describes how our variable moves over space and also as a function of the time. So the 1D steady state formula can be applied to various situations in almost all environmental compartments. Such models are especially popular in air pollution modeling. For example, in modeling the local concentration distribution due to emissions from stacks, but they can also be applied to problems of point pollution in rivers, channels, lakes, reservoirs, and the sea in ground and soil water. So most solutions are derived from the 1D solution for a plume, which is given by the normal distribution function. So this is a generalization, and it can take different forms. This is one of the forms of the Gaussian that can describe a Gaussian distribution. And this distribution is based on is coming from the transport equation, and in this case we are just considering diffusion, the diffusion term in transport, right? The initial condition for this solution is a peak with infinite concentration at x equals to 0. And this is this is also another way of looking at this Gaussian equation, and this equation is in terms of concentration. So the solution can be extended to the situation where the plume is transported within a flow field, and if the fluid moves with velocity v in x direction, this is the solution. So it means that we can have already a solution for our term, and then we can deal now with an ordinary differential equation. And we're going to model the pollution that is being emitted, sulfate pollution that is being emitted from a facility that is located away from the city, 10 kilometers away from the city, and is emitting a mass of pollutant at once. And then this mass of pollutant will start moving towards the city because of the air movement, right? So what do we want to do in this model? Your local air quality authority is concerned about whether this event surpasses the Australian air quality standards for sulfur dioxide, which are 0.20 parts per million for 1 hour, 0.08 parts per million for 1 day, and 0.02 parts per million for 1 year. To predict whether this occurs or not, we need to consider the initial SO2 and SO3 due to various natural processes, as well as the constant rate of chemical transformation from SO2 to SO3. So this is a small piece of one example that we discussed previously about also sulfate deposition and acid rain. But this is we're just going to focus now on the pollution of air. So we have a facility that will emit sulfate, and that sulfate will be received in the city. So our system, the boundaries of our system is is within the once it has reached the city. Everything is in terms of concentration, but to play with this, to a way to skip or to be able to do the model in terms of mass is to establish a fixed volume, a total fixed volume where we have where our system is where we are modeling our system. So in the case, this is something really like if we were working in a tank with a fixed volume, or we will be modeling the lake based on a fixed volume, then that volume can be used for the estimation of our stock flow equations. In this case, we're going to discuss a fixed volume of air that where everything is occurring, right? Where our process is occurring, and this volume is called our base volume, right? And we're going to have only the pollutant is entering our system, and then there is being transformed to SO3, and then it means that our stocks in our system, there are no need to have an initial value other than 0. So they can have a 0 value because they will receive now something that is feeding the stock, a constant value that is feeding the stock, and then eventually we will have a transformation that will increase this stock as well. Okay, so this is our the end of our lecture on examples. The examples will be provided in on the problem set, and some of these examples that we discussed will be provided in problem set number 7. And along with these examples, the MATLAB codes will help you to get familiar on how to start doing your own codes for your project number 2, and also for being confident about setting up your MATLAB codes for the preparation for the exam. It is worth mentioning that there are many resources on internet where you can actually find also other small and simple examples, and on dynamic models, environmental dynamic models. These include examples that are on the website of MATLAB, but also on the examples that are included on the books that we're using for this course.